I'm with a company called Armstrong Fluid Technology. Specifically, I work in the service business. Company many of you are probably familiar with. We might be a bit bigger than a lot of people know. We're about 1,100 employees. We've been making pumps and miscellaneous equipment since the 30s. And we're based here in North America. So a North American company with making products for North America here, either in the US or in Canada. So what I want to talk about, I want to give a little bit of context before I get right into the technical details around why this actually matters. Talk a bit about identifying the best candidates, what it means from an optimization perspective, again, more about pumps, what's involved in the baseline, what's involved in the optimization, and then talk about some stories, success stories, but also some things that may not have gone quite as perfectly as we would have hoped. So the building sector is responsible for in excess of 30% of energy consumption globally. It is the single largest end use of energy across the planet. It's slightly larger than transportation and slightly larger than industrial use. So buildings, and in that, commercial buildings are the biggest of the three. So there's absolutely a massive opportunity. And what's particularly disturbing is the existing stock is only being meaningfully retrofitted at a rate of 1 to 2% a year. So we're never going to get through the stock to have a meaningful impact on both the climate change and the domestic consumption of energy. And in the United States in particular, the market is ripe for upgrade. 75% of the buildings that are currently in use were built before 2000. And the ones that were built since 2000, the vast majority of those still use 1990 technology. So there's ample opportunity, and I don't need to explain to the people in this room just how much can be done inside the existing building stock in terms of retro commissioning, going back to existing buildings and squeezing out those inefficiencies. And HVAC in particular, which is topical since that's what we're here about, is playing an increasingly large role. So different studies say different amounts, but they all hover around 40%. And the reason why this is more meaningful than it was even 10 years ago is buildings are systematically working their way through lighting. Anybody that knows pretty much anything is doing a lighting project. And as buildings make their lighting systems more efficient, HVAC is growing as a percentage of the energy used in the building. So while it might not be growing in absolute terms, it is absolutely growing as a percentage, meaning that the people in this room have an outsized proportion or influence on the consumption of energy in commercial buildings going forward. So I talked a little bit about this intended to be a learning exercise. So from a pedagogical perspective, I thought I'd tell you what you're going to need to know at the end. What makes a good candidate for optimization? Certainly from our perspective, we would expect it to be an all-variable plant. And by all variable, we don't just mean variable speed, but we mean variable flow. And people often confuse, they say, yeah, I have a variable plant. Well, maybe, but you might have some pieces of equipment that are capable of variable speed, but not have the full variable flow experience. And to do that, we look technically for things that are headered or can be headered, so you can pump things in parallel and ultimately also get the benefits of what I'm going to talk about later, specifically pumps and towers. So technically, that's what we look for. Financially, if you want to make the project an easy sell, high cooling and run hours are obviously where we start. So Miami, easier to do than Seattle. Also, corresponding cost of power. So we don't really think that's news to anybody in this room. But what does it mean from a perspective of what you can actually get out of a plant? So the efficiency of a plant is largely dependent on not just the load, but the outdoor wet bulb. So I'm a little reluctant to say here's what the best-in-class efficiency number looks like, because it's really highly dependent on the prevailing weather conditions. So we kind of have a range. But typically, with the best-in-class, or at least good practice now, people still use PID loop, and the systems are still relatively siloed. They don't communicate that well, and they don't really integrate themselves from an operational perspective that well. So even if they have variable speed chillers, reset, a lot of things that people do now, it's still, you're probably got a system that's somewhere in the 0.75, 0.76 for the aggregate plant. There's been a movement, a little bit more integration, still PID, and still a fair degree of isolation or controlled variance between pumping and the cooling towers. a little bit more advanced reset, and they may have moved to a variable primary, and that's probably going to get them somewhere not a lot more than 0.7. So a good start, and a lot of buildings are doing that now, but ultimately it's not too difficult to get to a building in the zone of 0.5. And I don't want people to leave the room saying the guy from Armstrong said if I do this I'm going to end up with a plant that's at 0.5. But we have definitely seen plants that are considerably better. And it's kind of something that we think is a reasonably attainable number for things that have somewhat moderate climate, or so they're not in Louisiana, but they don't have to be in Phoenix either, to get something that takes advantage of all variable flow, and really sequencing the equipment so that it makes sense to run together. And it doesn't mean changing equipment. It's all about how you dispatch equipment inside of what you already have. So I'm going to talk a little bit about that. And ultimately, optimization is about a lot of things, but it's really about keeping chillers in their sweet spot. Chillers consume the most energy, and they also drive the efficiency of the whole unit. And one thing that we should be aware of is, I won't say I continue to be baffled, but I'm still surprised when I see identical systems, same chiller, same install date, same type, same operating conditions. 3 years later, one is substantially less efficient than the other. And that's not unique to chillers. That can be fans, it can be pumps. But just something has happened in the time from when that pump was chiller was commissioned to today. So this is an actual site somewhere in the Great Lakes area. I'm actually pretty familiar with the site, but they have, so I got my clicker, I got a 50-50 chance of getting this right. So on the top, the entering condenser water temperature, I got a less than 50% chance of using this clicker. So on the top, the entering condenser water temperature for the two pumps, highly similar. The load for the two pumps, because they were scheduled in parallel, very similar, but very different efficiencies across the entire spectrum. So part of optimization isn't about just taking manufactured published data and saying, well, this is how efficient that equipment is. It's about learning how efficient that particular piece of equipment is and making changes to how you dispatch and sequence that equipment, really reflecting what's going on in the plant. And as things change, you got to fine-tune the optimization later. So really recognizing that as a fundamental part. So nobody wants to hear me talk for an hour. Never. Under any circumstances. So this is the part where we have a little bit more interaction from the audience. So while every single project is different, if you had to pick a single piece of equipment where you would start, what would you typically consider first? Towers, pumps, chillers, or maybe you're not 100% certain. So this is also part of the presentation where I don't get offended if you spend a few minutes staring directly at your phone. So for all of you that have a phone, I would invite you to participate in this survey. So based on the questions above, you can either text. So if you want to text, you would text to 37607. It's not quite my entire name, Mark Gallagher, 604, and then you type in the letter, or you can go online to Poll Everywhere, and as you participate, we will see what the results are. So granted that some of you are over 30, we will allow another couple of minutes. So there is no right answer, but we will talk about what it means from a philosophy perspective in a couple of slides. So I see a few people still participating, so why don't I give you another 30 seconds and then we'll carry on with the presentation. Okay, so I think most of the people have started to answer, but really there is no right answer, but I do want to circle back. I am a little bit surprised at maybe the fact that I work for a company that's traditionally a pump manufacturer influenced your answer, but normally I get chillers as the first response. So this will play well. I'll have less heckling later when I get to the next slides. So perfect. So clearly, not quite 2/3 of you say you would probably start by thinking about pumps. So that's sort of either you read ahead because you picked up the flyer, or you this sort of plays well into the rest of the presentation. So I said I was going to talk a little bit about trends, and this slide isn't designed to tell you that phones went from big to small to big again, but really to convey that the evolution of technology is ongoing, and that two things. One, increasingly we're embedding technology into all equipment, and we are embedding internet connectivity into everything. Internet connectivity is essentially ubiquitous. And while we think we're at the forefront in pumps, really pumps are just a laggard industry. You know, the other components in HVAC have been doing this for a while, and the rest of the industries are light years ahead of where we are. So as an organization, we're excited where we're going, but there's still a lot left to be done. And the fact is that this is starting to change the way that we think that smaller components can have a different role inside the system. So as smaller components, pumps and valves and other things become internet enabled, they start to play a more meaningful role, not just in the control, but in the information and the diagnostics and how you make future decisions. So the analogy between phone technology and pump, valve, cooling tower technology is not really that much of a stretch. And the reason why, from a pragmatic perspective, why I think people should start thinking about it, maybe not doing the pumps first, but absolutely thinking about the pumps first, is they are without question the most financially attractive option inside the mechanical room, so behind lighting. I don't need to tell people that do flow balancing that balancing and appropriate flow absolutely is directly correlated to occupant comfort. And pumps and other pieces of equipment now provide insight that they didn't provide before. So you get insight from flow, which is one of the things that now embedded technology provides, that you're able to make improved future decisions. You get flow in the secondary system, you get flow on the condenser side, and even if you have a flow meter on the primary loop, you get to validate whether the flow meter makes sense. And increasingly now, as you move to more modular technology, making a pump decision now does not hamstring what you want to do with the chiller or boiler 2 years from now. So there's been a real evolution, and I don't want to spend a lot of time on this, but one of the things that I consistently struggle with when I'm talking to owners or utilities is just how big the savings can be. I don't want you to leave thinking, oh, I'm going to get 90%. But so other than lighting, it's one of the few technologies that can deliver up to 90% savings. And I know it sounds like a big number, and it's often we suffer with credibility until we actually sit down and explain how it comes. So the early technology was people would add a drive. And they had a constant speed, constant flow system. Somebody would add a drive and they'd figure out they could slow the pump down. Same constant speed pump, just running a little bit slower, less throttling. That was a good first start, but that's kind of early 90s technology. And then somewhere later, people decided, well, we still want to move to variable flow. Most of the savings come from moving to variable flow. And if you have a mechanical room sensor, because you need some kind of feedback mechanism, you're probably getting half the savings. So you've got a substantial savings. Then the rest of the savings start to come from how you control the pump, how you can fundamentally control the pump differently by letting the pump control itself. I know it's a bit of a mind shift for some of the people, specifically if you come from a BAS industry, but pumps running themselves makes a lot of sense. They can decide what speed and what set points work for them based on the efficiency and the control logic in those pumps. And then the rest of the savings really come from sizing, and then ultimately some component efficiencies, but really comes from parallel pumping and adding it all together. So it's components, control strategy, sizing, and parallel. So really that's kind of it. All sorts of new pump technology being driven from European standards. As a manufacturer, if you go through the trouble to comply with the European legislation, which is almost always more stringent, you might as well sell the same product everywhere else. You got all the R&D costs done. You've changed your manufacturing, so you might as well sell it elsewhere. So European legislation is driving motor and pump efficiency from everything from fans to pumps to escalators. And built-in parallel pumping, this is not a new concept. I talk about it like it's new, but this is being available in Europe since the mid-90s. What is different is built-in parallel pump dispatch technology. The parallel pumping is kind of the norm in a lot of markets at the moment. But like I talked about earlier, embedded technology and diagnostic insights, that's not unique to pumps, but I'm here obviously talking about how that fits into optimization. I said I was going to talk about parallel, and the reason why I want to talk about parallel is not just because parallel is important for pumping, but it's really the fundamental building block for other aspects of optimization. And not wanting to do a bait and switch, because I just 20 seconds ago said I was going to talk about parallel, and then I show a slide that says sensorless. But sensorless is an underlying control strategy that allows for more effective parallel pumping. And I no longer assume that when I'm talking to people, they know what sensorless actually means. It's pretty much the only thing we sell in the UK, and it's mostly what we sell in Toronto, but it's mostly not what we sell in the United States. So I'm going to assume that some of the people in the audience don't know how sensorless technology works. So we introduced this in 2002, and we are no longer the only company. Lots of companies have a comparable approach. But sensorless means no sensor. It's not a fancy marketing term like I would have normally used. It means there is no sensor in that system. There's no DP sensor required, and there is no flow meter required, because the pump will calculate the flow and the head based on the speed and the power. So for every single speed and power point on a pump curve, there is a corresponding flow and head. So if you map the points across the operating parameters of a pump in the factory with the speed and the head, or the speed and the power, amp draw actually, we will have a corresponding flow and head. And in the field, the pump acts the same way as it did on the test rig. So the pump in the field will measure speed and power, and it will operate at the same flow and head as it did before. So based on speed and power that we get from the drive, we calculate and present flow and head, and it's amazingly accurate. So we've shipped over, it's not just about us, the industry has shipped over 50,000 units using this technology. So it's not brand new, and it typically depends on the slope of the curve, it's always within 5%, but depending on the actual interpolation, in many cases it's within 2% accuracy. So it gives you a reading that should be, more than sufficient for most flow applications. So ultimately, it mimics the way a sensor would act in the field. The pump senses the changes as the valves open and close, the pressure changes, and the pump will slow down or speed up based on the way you've set the parameters. So constant flow, constant pressure. You can have an operating range. You want to have a minimum head, have a GPM inside this range, and it will slow down and speed up to furnish you with the flow or the head that you need based on the parameters that you've dictated inside the pump.
How do you know system curve? How do you know system curve?
So the system curve.
That's what you're supposed to be floating on, not what's on the side of the curve.
Correct.
So how do you know that?
So the system curve, so that's an excellent question. I wasn't actually going to get to that. But so for people that didn't hear, the question was, how do we know what the system curve is? So the answer is, we don't know what the system curve is until you ship the pump to site. But what you will know is you will know what the required flow is, or the expected flow based on the equipment that you have.
It all depends on the pressure, which you don't know.
Correct. So the point is, you don't know the pressure until the pump shows up to site. But we will know what we want the pump to operate at in terms of delivered head. And it will simulate the same. The system curve, should have brought a more technical presentation. The system curve will, when the pumps are really set up, when the valves are open, so you hit the flow balance button, and it will measure the actual head of the system based on the resistance that it notices at that time. And it will remap the curve for that particular application at that time. So if you have a minimum, if you set the minimum head of 40%, then you think that 40% of 80 feet, or 100 feet, so I can do the math in my head. So 40. But if it's really only 70, then it will be 28. So it will remap the curve based on what the system curve is. So I know I often have a lot of skeptics. So this is not unique to this organization. This is not something that I'm trying to portray as brand new, but it sort of underpins the rest of the technology. So it's sort of why I slide it in so that people understand a little bit more. Because as an industry, we've shipped in excess of 30,000, we've shipped in excess. I know the industry has shipped over 50,000 devices that are currently operating in the Americas and in Europe using the technology. So it is a little bit of a mental shift for many, but it sort of underpins how you get to the other aspects of parallel. So I do have a couple slides on parallel. How am I doing for time? Doing almost within 3 minutes of where I should be. Probably 25 minutes longer than you wanted so far. So on this slide, so this is probably the most technical slide I have. So if you want to tune out for 2 minutes, that's okay. If you're really interested in how parallel pumping, pay attention to this slide. This slide is probably the most indicative slide I have of how parallel pumping actually works. So on the bottom of the, well actually I was going to say on my left, but also on my right, is the traditional approach to speed-based control. And this is not just pumps, it's fans, chillers, pretty much everything. The way BAS systems traditionally work, and still work in the vast majority of buildings, is that they will ramp up the equipment to somewhere between 90 and 95%, maybe 100% capacity, before they dispatch or sequence a second piece of equipment. It's just speed-based control is the way things have been working. And it works fine. Technically, it works fine. And then on the top, we have what we would do with parallel pumping, or parallel dispatch of any equipment. So in the first situation, both pieces of equipment will run up to about 3/4 of their speed. At which point, on the bottom, the traditional sequencing will, so you get the same flow in either situation. The flow is the blue curve on both graphs. In the second situation, on the bottom, it will run that pump right up, or that chiller, or whatever it is, right up to maximum capacity, way past its peak efficiency. So anything that's designed for part load will be more efficient at a part load operating point than at a full speed condition. So the way we would recommend and the way we would sequence things, or in others, is that based on the marginal efficiency of the particular piece of equipment, a second piece of equipment will come on and keep them as close as possible to their optimal efficiency. So 2 pumps versus 1 pump on the bottom. Same thing happens. This little caution sign is for the next slide to indicate the biggest difference in efficiencies. Same thing will happen, and on the right, the power of the 2 pumps consumed will far exceed the power of the 3 pumps will be much less than the power of the 2 pumps. So ultimately, if you run everything flat out, there's no savings. So when you get 3 pumps running, whether with a traditional staging or a more contemporary approach, there's no savings if the building really is at full load. But we also know, generally, and certainly according to Ashway, 90% of the time, buildings run less than 60% load. And on the very next slide, this is a building in the Great Lakes area. And it's not a nice bell graph. It happens to be real data. For that particular location, we have 2 towers. They happen to be condos. Identical buildings with identical equipment, happens to be our equipment, that one ran via a fairly name brand BAS supplier, and the other ran in parallel. And based on their particular profile, they save 34% just in parallel dispatch. Exact same equipment, exact building next door with a shared common lobby. So that doesn't mean everybody's going to save 34%. It's entirely dependent on the building condition and the building load, but I think 30% is probably a reasonable mean. So sort of substantiating that, last year we changed some of our pumps in the tower in downtown Toronto, happens to be a hotel, that were 4 years old, put in the new pumps, ran them in parallel, and they saved 40%. A little bit of that's from hydraulic efficiency, but mostly it's from parallel pumping. And the same, I know I'm talking about pumping, but the same approach to using parallel technology applies to all equipment in the building. And ultimately, driving equipment, sequencing equipment in parallel and or in harmony with other pieces of equipment in the building makes the building more efficient. So I talked a little bit about one of the learnings is what do we need to know? And absolutely, we need to know a baseline. So unlike lighting, where how, what's the operating hours multiplied by 87%, and you got some savings number that's pretty accurate. That's not the way it works in mechanical systems, not even closely. So this is the same building I showed earlier with the 2 chillers that were grossly different in their efficiency. So notice they never get close. This is a full year's worth of data. They never got over 50% of the capacity that they had in that plant. So they have 4 big chillers, never run more than 2, ever, 0 chance. But the plant has a dramatic improvement in efficiency as they approach 50%. It really, somewhere around 25% total load, it kind of starts to plateau a little bit. But it's all about how they sequence equipment. So this was a baseline. So it's really about establishing baseline, not for just the chiller, but the equipment in its entirety and how it works as a system. So I'm going to talk a little bit about baseline later. I also know that this is another point where you guys need a break. So this is the next part where we ask for guest attendee participation. So critical data sets that we would typically look for if we could get everything: kilowatt draw, speed, all the equipment, run hours, flow, supply temperature, return temperature, entering condenser temperature, leaving tower, outdoor air, and humidity. There would be more things, but those we would consider really a base set of data that we would want. But if you had to leave one of them out, so let's say you couldn't get all that, and on this list, speed, run hours, flow, temperature, or humidity, which would you be more inclined to leave out? So if you had to omit one piece of data, what would you leave out? It's a bit theoretical, because typically we collect all of that, but I think it begs some further discussion. Definitely more adept at the concept of doing the survey. Give you another 15 seconds. I think most people are already done. So, make a fibber out of me. So, there is no right answer, but I think there are better answers. I would probably agree with the most common answer. I would probably leave humidity out. I think all of this data is important. I'd probably leave humidity out. Absolutely outdoor air, very important. I happen to think flow, I agree with the people that pick flow as the least, or the most important, the least likely thing you're going to leave out. I might leave equipment speed out, because you can often interpolate equipment speed based on power draw, but speed is important too. Run hours, I happen to think that's pretty important, but it totally depends on how else you calculate the information. But generally, I think there's some degree of consensus that flow is very important and humidity is slightly less important. And the reason why that matters is kind of a little bit evident, but it's about flow. So using equipment to give you built-in flow validation, very important. And where do you start? Where do you start with an optimization project? I do want to actually get to how the second part of the course around optimization, and it really depends on where you are at the moment. There is no right answer. It's all about taking stock of what you have now, where the building is going to be from a tenant perspective, what the owner wants to get out of it, and the equipment and what else they have. But ultimately, I'd like to challenge the people in the room, although I don't need to challenge you too hard because many people implicitly agree, that pumps are a logical place to start, and then squeeze out the inefficiencies that exist in the system. So squeeze out the efficiencies in the rest of the equipment before you make a decision what else to replace. So you might need a new cooling tower, you might need a new chiller, you might need to repipe the mechanical room, but see what you can get out of your existing system before you make that decision. So the people in this room might not actually get to make that decision, but certainly you have influence. And rather than spending $750,000 on a new chilled water system, you might get half the savings without doing any major capital upgrade. So really it's about taking advantage of what you have. And identifying the best candidates, as we said earlier, about all variable. Really, once you get to variable speed and variable flow, you get to all sorts of savings. Configuration, and then on the bottom, the financial run hours. Of course, there is always an exception. In the unlikely event anybody actually are familiar with this building, they only have one chiller. This is a one chiller application, which normally I would say, probably not the best candidate. They, however, save a lot of money simply on the condenser side optimization. And they were very happy, continue to be happy, and they noticed a very substantial reduction. So while there are obvious choices or obvious places to start, clearly there's some candidates that should be not overlooked. So ultra-efficient optimization is about all variable. Really, we look for centrifugal chillers, much easier to modulate than screw chillers, or certainly absorption would be a different challenge totally. We want to work with the BAS system as an industry generally. We don't want to, this is not a threat to the BAS, it's about complementing what you already have. And consider the whole plant, condenser, pumping, whatever aspect. You don't have to make the whole decision. You can do smaller pieces as a start. Typically, we would see 15 to 30% savings, and that's a pretty defensible number depending on the way it works. So I talked a bit about optimizing what you have. Optimization is, how many people in the room golf? Okay, some. So the analogy might make sense. Optimization is kind of like getting a really good caddy. So if you have a BAS system, everything looks like either a driver or a 5-iron. So having a good caddy, if you're on a hole and you pull out your 5-iron, because that's your standard club for this, it's 165 yards downhill. It's 165 yards, that's the only thing you're looking at. But if it's 165 downhill with the wind at your back, and on the other side of the green is a nasty pond, maybe you want something else. So optimization is really about making sense and making decisions that make sense at that time based on the unique parameters that you're experiencing. So whether that be a change in the load, a change in your specific efficiency of individual equipments, and it's about working with the BAS to make better decisions. So the BAS continues to control the variable primary side. It continues to sequence the chillers. The chillers will sequence themselves based on speed. So you can see how many chillers to run. And then the chillers will ramp themselves up or down inside their technology. And they will run themselves with the embedded technology in the chillers to make sure that they stay inside their safety zone. So they don't stray outside of their desired set point. And what's required? There's not a lot of changes required of the BAS. There's fewer than 20 points that need to be harmonized. For those that really want to take notes, number of chillers running, number of towers running, number of fans, fan speed, condenser pump speeds, chilled water pumps, chilled water speed, and chiller supply set point, and that's it. So those are the points that we would need to get, and then we send this speed recommendation. So this is not unique to our organization. Shoot. Give away the next slide. So now I'm all flustered because the suspense part was ruined. So the next slide. So this, I have a couple. We're getting to the stories now. So this story is one of the earliest applications we did, and I like to talk about it because there was no equipment change. The only thing this site did was introduce the algorithm and how they dispatch their equipment. They already had an efficient plant, very efficient chillers, happened to be in the southwest, very dry, lots of natural efficient cooling. I was going to get you to guess the time when we turned on the algorithm, but you can probably tell. So visually, it's pretty impactful. And over the course of the first 12 months, which was the only time we measured it, they saved 31%. So it was almost instant. They could see the drop, and they could see it sustained. So this one I like to talk about because there were no other changes. There's nothing else in that building changed other than the way they sequenced equipment. And they had already set everything up. They had chillers that could run in parallel, they had variable flow, and they had a pretty decent cooling tower system. So I like to talk about this one because I'm sure most people have some sympathy. Not every project goes as expected. I'm putting this one up because it didn't go as expected, but it ended really well. They're actually pretty happy. So this one we set up in August 2014. Happens to be Whirlpool, like it says. We didn't actually sell the project. The company that sold the project didn't do a baseline. It said, we're going to do this. We're going to save a bunch of money. So they gave an estimate of what the existing baseline was. So we didn't come close. We didn't even get within a mile of what they thought they were going to end up with as an efficiency per ton. But what happened was they realized all of the savings and more in absolute dollars, which was subsequently substantiated by the local utility. So the owner was actually quite happy. But in the absence of a baseline, their original estimate of how efficient the plant was completely bogus. It wasn't even close. So they realized more savings, but they never got to the efficiency level. They thought they were going to get to a 0.7 something. We had a hard time getting them down to 0.9. But, because I remember they actually called me and said, this is not working like we expected. And we explained, and we went through, and we actually had a lot of logs around, because the owner, or not the owner, the operators were skeptical, so they kept turning it off. Which was, in hindsight, happened to be perfect for me, because we had a natural experiment as to when they were running it and when they weren't running it. And we showed them that and the utility and said, this is ideal because here's when you consciously turned it off and here's what happened. And here's your actual baseline. It was like 1.6. So, and here's what you are after. And so it corresponds with what they ultimately ended up saving, which made the subsequent conversations much, much easier. So the utility substantiated, they gave them $60,000. They saved about $54,000 in what was the core project, but the real hidden benefit was they had a free cooling system that was entirely binary, on, off. So when they went to switch free cooling, all fans, all pumps, 100% speed. There was no, it wasn't connected to the BAS. It went on, so it didn't matter if they needed 50 tons or 200 tons. Everything went to full speed. So we introduced the same kind of modular concept for that. And they got a bonus $32,000 just through thinking a little bit differently. So they were actually thrilled. Obviously, that's part of the reason why I talked about them. But part of the course, this is a course, so you're actually getting credits. So you have to sort of pay attention. You have a moral obligation to pay some attention. Not everything goes perfect. And there are pitfalls, and we as an organization, especially some of our earlier projects, here are some things that I didn't put in the presentation, but please remember, send somebody to site who knows something about piping and valves. Don't just assume that everything's fine. Some of the worst debacles I've seen were when we showed up and things were like not even remotely similar. So we did an optimization project, and some of the issues are not unique to the United States. There's some pretty not smart Canadians. So we, being from Toronto, I know a lot of them. And so we show up at site, and there's one isolation valve. So there's 3 chillers supposed to run in parallel. One isolation valve for one chiller, and one isolation valve for the other two chillers. So we can never get it to work right until we go back and realize, oh, there's no valve. So the one chiller runs 60% of the time, and when we want parallel, we run chillers 2 and 3. And that's just the only way it's going to work. So they have a disproportionate number of run hours on that one piece of equipment, and it's going to be like that until they eventually pay. And we had another project. The other thing, so item 1, look at piping and valves, and look at cooling towers. Cooling towers is the next bugaboo. So we had a site, happened to be in the U.S. We could never get the condenser water temperature back to where we thought it was supposed to be. The return temperature too high. So somebody went back to site and said, oh, I know why. Because there's a wall. The cooling tower is against the wall. So it was starved for air. It was like gasping trying to get air because they built it. The building next to it complained because it was ugly. So they built a screen so that the people wouldn't have to look at it. And then to compensate for that, because they go like, this isn't working well, they piped air in from the underground garage. I'm not the smartest guy in any room, but I know that didn't help because now they're piping all their warm exhaust air from the garage into the cooling tower to give it extra air. So they get all the superheated air from the underground parking garage piped into the cooling tower. And so we explained to them that wasn't helping either. But going to site and looking at some of these things, don't assume that things are as the customer projects. We did a project in Toronto, also a cooling tower debacle. We couldn't get it to work. Cooling tower wouldn't give us the return temperature. Finally, we found out it's connected to the next building as well. Originally, these two buildings were owned by the same company. It was an old heritage building that was connected to the heritage building next to it. They shared a cooling tower, but they subsequently sold the next building. So I don't know how that worked from a real estate transaction, but it was complicated from a sequencing perspective. So look at the systems, have somebody that understands cooling towers and piping, because those often come back to bite you. And I know this is a bit like talking to the people that know 10 times more than I do about this, but I just feel an obligation to mention it because it's not as it seems. And it's not that customers are trying to be deceitful. It's just often they don't know. They just don't know there's another loop. They don't know that there was a meter installed 10 years ago when it's being disconnected. And you can't trust the baseline data from the BAS. It doesn't mean it's going to be wrong, but it might not be right. That flow meter might not have been calibrated for 15 years. And so you'll get data that you think this is the building load, and it's nothing like that at all. Right? Or the DP sensor might not have worked properly for 9 years, and people can't find it anymore. So when you get data that you want to use in the baseline, make sure that you have something to calibrate it with. And partly because this is a course, this is my last slide, this is where you get to add value. So these are 3 scenarios. One of them is a little bit of a gimme, and the other 2 might require you to think. And this is where I actually encourage you to read for a second. But the scenario 1, 2 750-ton variable flow. Primary pumps are variable speed and header. Secondary, also variable and header. Condenser pumps, constant speed, very common. That's typically what we see. And tower fans. So on the surface, sounds like a pretty good site. A bit smaller. But if you had to pick between that one and scenario 2, assuming they have the exact same load, how would you make that decision? So you've got larger chillers. They are variable speed compressors, but they're constant flow. And they've been sized for duty standby. And the variable secondary also constant variable speed, but essentially constant. The primary pump's variable speed, and it's constant speed, but dedicated condenser pumps. So this site's going to need a fair bit of work to make it in an optimized perspective, right? You're going to have to change the header on the condenser pumps. You're going to have to look at the chillers, because not all chillers, this is the last thing you probably already know, but you should remember, not all chillers that are variable speed handle variable flow very well. Older chillers, just because they have a variable speed compressor doesn't mean they like variable flow, especially on the condenser side. So variable flow doesn't always make chillers run better. Pretty much universally true for new chillers, not always true for old early generation chillers. So somebody might have put a variable speed drive on it, and they think you can now optimize it, but you're just going to maybe wreak havoc on the system. So you need to understand how that chiller behaves with variable flow before you do an optimization project. And you also need to know the sizing of the chiller, because if you have two really grossly oversized chillers, you're never going to get to run them in parallel. You're just going to have two chillers with new technology where one runs and the other's in standby. So the sizing is a very important consideration before you make a big investment in doing something different. And that kind of leads back to why you use the pump and the flow, or just the flow data, to start making decisions on equipment sizing. Equipment sizing is a very important part of the equation. So, and number 3, I'm hoping you realize that's kind of a gimme. If you have all variable, it's all headered, and you got 3 chillers, you know that they built in 3 for at least 2 to run in parallel. I can't think anybody would put 3 chillers with the expectation they were only ever going to run 1. So that's kind of a gimme. I think the audience participation is at its limit at the moment. So that is your credit course. You do have 8 minutes left, or as long as you want. About 8 minutes left in this room to ask questions, given that there were minimal interruptions. Yes, please.
Real quick, would you speak to, with your experience, what is the best combination for saving energy with chill water reset temperatures, so that you run lower chill water, and then in combination with leaving area resets? And I know it's dependent on the building size and how many fans you got and how much air you're pumping and all that kind of stuff, but in general, the other 2 variables that we're not speaking to is what temperature we're running the chill water and what is our leaving air temps, and how that works in a bigger system, large buildings like you've shown, because that affects your flow in the end. And so what's your experience with those other opportunities to save energy?
Right. So the question is, do I have any insight or projections, comments around the combination of chill water supply temperature and air handling fan, and how you handle that out in the zones? And that is a little bit tricky. Generally, although it's not universally true, we would think if the building can accommodate a slightly higher supply temperature of water being furnished and a little bit more fan power, you're going to come out ahead. So that the building will be more efficient. That's not obviously always true, and you have humidity issues, so you have set points that you need to do or reach to supply and get a reasonable return, so you don't leave the buildings cold but not dehumidified. But then too cold, well, you just have massive fan power savings. Anything below 43, really, most chillers really don't like that. 43 is kind of a number that most chiller manufacturers don't want to have supply temperature colder than that. There are exceptions, but that's kind of and so reset, the way that we would reset is based on load, not outdoor air temperature. So load is often related, but not always perfectly related to outdoor air temperature. So we would have that based on return water temperature rather than outdoor air or humidity. So I haven't really answered your question because it's a complicated answer.
When you were talking about the smart pumps, and they know the flow based on the curve, can you connect the BAS and get that information out of it so you're seeing what the flow is?
So the question was, can we connect the pumps and provide flow data to the BAS? That's a super simple answer, yes. That's been available for years. So pumps will provide flow, head, speed, and power, and run stats. And most of our competitors will provide that in BACnet or Modbus. So that's yes.
Yeah, you don't need flow meters to...
Different degree of accuracy, but many will provide flow data as built in for integrated pumps. So that's not a unique proposition.
Okay, so that brings me to another question. If we're out in the field, we're doing the TMB on the pump, is that data available on your website or something, so that we don't have to constantly try to guess what my real performance is?
Right.
I mean, if your pump curves are greater than 2% and I can't get one piece of the data, if I could log in and put in the model number, and put in the speed or whatever, and you put it through the parameters, you can tell me the rest of it.
Okay, so this guy's not a plant. The question was, can we provide this data over the web? I wasn't going to mention that because yes, we sell that. That's a service,
Okay.
along with all the other diagnostics. So I thought that started to sound like a commercial. Yes, but that's a paid function. All right. Well, thank you. Thank you for your attendance. Please make sure you pick up an evaluation. I know the organizers would appreciate that. And thank you very much for your time. Enjoy the rest of the conference.